This particular video episode, we're going to attend to and address the concept of deviation from ideal gas law. This would be circumstances under which the ideal gas law and the accompanying laws of Boyle's, Charles, Gay-Lussac combined gas law are not followed perfectly. A key thing here is that for gas laws to be followed, we have to make sure that our gases are actually following the kinetic theory of gases. The key feature of the kinetic theory of gases would be specifically, amongst all of them, that attractive forces between the particles are negligible, which is what allows the gas particles to behave as independent particles. In this picture, what we can see is we have a container with gas particles that are all behaving independently of one another, and that they're not sticking together. They're ricocheting and bouncing off the sides of the container. In this circumstance, when all the particles are independent of each other, we can say that the gas is ideal and all the gas laws are going to be followed when gases are behaving in this fashion. So in this case, if the gases do not follow the kinetic theory of gases, then the gas laws are no longer followed, and we see what's referred to as deviation from ideal behavior, and we see deviation then from the gas laws. An example of this would be the circumstance when the attractive forces between gas particles are no longer negligible and the particles actually start to stick together slightly. This would cause deviation from ideal gas behavior. Going back to our earlier picture, an example of something when we have ideal behavior, all of the particles in the gas are behaving independent of one another. In this case, the container has 10 particles. And so the gas laws, it would be as if there were, let's say, 10 moles of particles in this scenario to follow the gas laws. Now, if we begin to lower the temperature, that's going to cause the particles to move slower. And what can occur is now when we have a couple particles collide, when they collide, rather than ricocheting off of one another, what occurs is the particles now stick together. And instead of behaving as two particles, this is now behaving as if it's only one particle bouncing off the walls of the container. The effect is, as these particles begin to clump together into little groups of 2s and 3s, which is still small enough to the eye, it'll appear as if it's a gas to us. But what happens is in this container, we now have 1, 2, 3, 4, 5, 6 particles is what the walls of the container are seeing or experiencing bouncing off of them, instead of the actual 10 particles that exist in the container when the gas is behaving ideally. Because we're having only 6 particles instead of 10 particles bounce around off the sides of the container, we're now going to see some deviation occurring from the ideal gas laws. The gas laws are based on 10 particles for this amount of gas bouncing off the sides of the container, but as they begin to stick together and they still behave gaseous to our eye, this will look like a gas. The particles are not large enough yet sticking together to form droplets and liquefy. This is going to cause deviation from the ideal gas law. What then occurs as we continue to take the temperature and make the temperature drop is the clumps of particles will enlarge, and we get clumps of 5, 6, 7, or 8 particles now sticking together. As the particles get large enough, gravity takes over, makes them fall down, and these large clumps of particles, when gravity takes over making them fall, That's when we get the process of the gas completing its phase change as the gas turns into a liquid. Deviation from ideal gas behavior occurs under several different circumstances. Low temperature, high pressure, or a combination of low temperature and high pressure. High pressure works in that if we could take a container and squish the volume down on the container, so that as we push or squeeze our volume down, the particles now end up in such close physical proximity that some of the particles, the attractive forces now become strong enough because they're packed so closely, it's going to make the particles clump together. And when they're in groups of 2s or 3s, they're bouncing off the wall as if they're one particle, but it's really 2 or 3 stuck together. And again, we get deviation from the gas laws under these conditions. Now, just for an example, let's say we have several gases. Gas X has a boiling point of -20 Celsius, Y has a boiling point of -100, and Z's boiling point is -200 degrees Celsius. Now, the boiling point of something, that's the temperature at which the gas to liquid phase change occurs. Let's say we're under normal conditions, where room temperature is about 25 degrees Celsius. All three gases, X, Y, and Z, will appear to us to be gaseous under these conditions. Now, as we start to lower the temperature of the room, the first gas that would liquefy would be X. So as we drop the temperature, X would be the first one to show deviation from ideal behavior. In fact, because X is pretty close, 25 degrees and -20 to when it liquefies, at 25 degrees, X may already have some deviation from ideal behavior. Whereas Y, because it changes into a liquid at -100, it's quite a ways away from turning into a liquid. This will be a perfect ideal gas at 25 degrees. And likewise, Z will also be a perfect ideal gas at 25 degrees Celsius. So as we cool something, as we drop temperature, and the temperature approaches the point at which something turns into a liquid, we'll get more substantive deviation from ideal behavior. Y and Z in this circumstance, because the point at which they're going to liquefy is so far away from 25 degrees Celsius, again, these will demonstrate ideal behavior, whereas X, because the proximity of when it's going to liquefy is fairly close to the actual temperature, X is going to start to show some deviation as some of the particles will begin to clump into groups of 2s and 3s as the temperature begins to drop.